Hello everyone! Welcome to this introductory video on inverse stereolithography. My name is Lisa Reinke, and in the following 15 minutes I'm going to introduce you to the most important facts and key concepts of inverse stereolithography, or short iSLA. Usually at the end of a presentation you get the chance to ask questions. Since we all experience a new situation, this presentation is a little different. As I myself struggle sometimes with asking questions in Zoom, I prepared a little quiz for you. Maybe this helps you to find things I did not explain detailed enough and how to ask for them. I would be happy if you tried it out after I finished. More about this at the end of my presentation. I divided my presentation into two parts. At first, I will explain inverted SLA in general, concerning the process, its up and downsides, and information on iSLA materials. In the second part, I will introduce Formlabs, one of the most prominent iSLA manufacturers globally. Without any further ado, let's dive into the iSLA process. Stereolithography was the very first additive manufacturing technique to be invented. It all started in the early 1970s. Japanese researcher Dr. Hideo Kodama invented the stereolithographic layering process, in which a UV laser is used to cure photosensitive polymers. In 1986, Chuck Hull filed a patent for stereolithographic machines and founded 3D Systems, the company which Armin will tell you more about. Only 2 years later, Hull invented the STL file format, which is the basis to 3D print design. In his original patent from 1986, next to the standard right-side-up SLA, he also described the process of inverse SLA. A sketch of his early apparatus is shown on the right. This might look a little complex, but let's take a closer look on how it works. SLA belongs to the family of wet polymerization techniques. The setup is very simple. The machine consists of a tank or vat for the liquid resin and an optical system which controls the movements of the laser. The tank is filled with a liquid monomeric resin. Depending on the application area of the finished part, different resin formulas can be used. More of that later on. At the beginning of the process, the building platform is lowered by a Z-stepper motor. It presses excessive liquid away so that only the desired layer thickness stays in the bottom of the tank. An ultraviolet laser hits this resin layer on desired areas. In case of inverse SLA, the laser comes from below the resin vat and passes a transparent window. When hitting the resin, the laser excites the monomers. This leads to a polymerization chain reaction in which the monomers start to link to each other. In the end, the liquid resin becomes a highly cross-linked 3D network. All in all, the material state changes from liquid to solid. An optical system consisting of lenses and mirrors guides the laser beam on specific x-y coordinates. Only selected areas of the resin are exposed to the UV light, and therefore a shape is generated which forms the contour of the current layer. After creation of the first layer, the building platform is moved upwards. This step is called peeling because the cured layer has to rise out of the liquid resin. This has to be done carefully. During the peeling, high stress is applied to the printed layer and may cause delamination. In this time, new resin flows below the already printed layer. When the building platform is once more lowered, the procedure can start again. By repeating the process, the object is built layer by layer and upside down. As it still might be a bit hard to imagine that upside down idea of the process, here's a short descriptive video on how the production of a complete part looks like. The printer shown here is the Form 3, provided by Formlabs. This orange shield is to protect the user from the UV radiation. The column you can see here is the Z-control. The building platform moves up and down across this axis. The downside of the platform is flat and polished so that the first layer can stick to it. The resin vat, which you can see here, is relatively small because not much resin is needed for the layer formation. This is the transparent window which is passed by the laser. Once the design file is uploaded and the resin is filled in, the printing can start. The platform moves down, and here you can see how excessive liquid is pressed away. You can see here that the laser only hits desired points. When a layer is done, the platform moves up and down again. Formlabs invented a special method where the layer does not leave the resin bed completely to reduce stresses applied to the layer. At the end, the finished part looks like this. You can see here that the actual top part of the flower points downwards, so this part is oriented upside down. When the printing is done, the post-processing follows. The first thing to be done is the post-curing. This is necessary because the printing is not performed under vacuum. Therefore, oxygen is present in the building chamber, and oxygen is a polymerization inhibitor. In a completely unhindered curing process, the purple monomers together with the pink photoinitializers form a nice and stable 3D network. In contrast to that, an inhibited process turns out differently. Under the presence of oxygen, represented here by the gray shapes, the network will not be as stable because the oxygen molecules react with the photoinitializers and stop the chain propagation. This means small portions of the resin are not completely cured after printing and need to be post-cured. After the post-curing, the object is rinsed to remove any resin residues. Then the most time-consuming post-processing step follows. As you can see, the finished part comes out with a lot of support structures. They are needed because in iSLA there is no support material which could hold the printed layer, as for example in the powder bed printing techniques. And since it is not possible to print more than one material at a time, the support structures cannot be made of another material. This means washing away, like in some FDM printing techniques, is not possible either. The support structures have to be removed manually. The major potential of iSLA is the vast material variety which can be used for printing. There are many different resin formulas, each designed for specific applications, but all resins have some components in common. At first, there are the precursors, or prepolymers. This is the monomeric base system, consisting of thermoset monomers. They can form strong covalent bonds and chains. Once bonded by UV light, this reaction is not reversible. Two main base systems are commonly used. For fast printing, acrylate resins are preferred. They show high curing rates and can be modified to achieve different mechanical properties. But they show high shrinkage and therefore can cause distortion of the finished object. Also, acrylate resins are very sensitive to oxygen. Another resin type are epoxide-based systems. They have the advantage of being stable against oxygen and show lower shrinkage, but they are unstable against moisture. The second ingredient are photoinitiators. They are of great importance because they determine the rate of the curing and also the light sensitivity of the resin. They are responsible for the cross-linking density and therefore affect the mechanical properties of the finished part. There are two types of photoinitiators, radical and cationic. The radical initiators are used in acrylate systems. They absorb incident radiation and lead to radical formation, which starts the cross-linking chain reaction. Cationic initiators are usually used in epoxy systems and form cations instead of radicals. The third ingredient are the absorbers. They limit the curing depth. This is especially important to enable complex geometries with undercuts and areas which should not be cured, and also to reduce aging effects by UV light. Most commonly, benzotriazole derivatives are used. Last but not least, fillers and additives can be added to the resin. They are used to influence mechanical, thermal, optical, or even electrical properties of the part. Additives are also used to obtain better flow parameters of the liquid resin because they can reduce the viscosity. The problem with fillers is that they can show a different diffraction angle than the rest of the matrix. When the laser hits an area with a high filler content, it might be deflected. This can lead to printing impurities and failures. When adding fillers and additives, the refractive index difference therefore has to be considered and minimized. As in all 3D printing techniques, part quality depends greatly on the material choice. Although for iSLA there are extensive resin libraries and there is active research done on new compositions, some application areas are better suited for iSLA than others. If the finished part has to fulfill high demands concerning resolution and surface finish, iSLA is a great choice. Layer thicknesses of down to 10 micrometers are possible because scanning speed, laser power and Z-stepper motor of the building platform enable high control on the curing depth and therefore the vertical resolution. The lateral resolution, or curing width, is mainly influenced by the laser spot size, which can be easily controlled as well. This enables the printing of highly personalized products such as dental implants, hearing aids or other prostheses, where the geometry is highly adjusted to the patient's body. Also, when the part has to be strong or flexible, or when different materials need to be tested out, iSLA can be used because there are many different resin formulas present. And where layer detachment must not be a problem, iSLA should be the method of choice as well, since the layers are chemically bonded. This also leads to isotropic properties of the finished part, which is a great advantage compared to other techniques such as FDM, where anisotropy is a major issue. The upside-down approach furthermore limits the material consumption. The tank has to be filled only a little more than the desired layer thickness, which also leads to less waste production. The lower image shows the right-side-up approach, where the platform moves down during building. This means the tank has to be filled completely to cover the whole object. Considering all those benefits, iSLA still is bound to certain limits. The parts cannot be as big as in other methods because the building chambers are not scaled for big part printing. iSLA is not suitable for great series production because it requires highly time and cost-intensive post-processing, where the parts have to be post-cured and the support structures need to be removed. Parts which experience high exposure to UV light should also not be printed with iSLA, or at least have to be coated against the radiation. As the resin is sensitive to UV light, it is also not endlessly stable. High exposure can lead to color change, curling, and even brittleness of the part. Although there are many different resin formulas, right now it is not possible to print more than one material at a time, like it can be done, for example, in injection molding. So for the production of multi-component objects or colorful parts, iSLA is not suitable, or only at a cost of additional production steps. Now we know about the basic principles of the iSLA process and the materials. The system itself has not vastly changed from its beginnings, but let's take a look on how iSLA managed its way into industry. In 2011, 3 MIT Media Lab students founded Formlabs. Their company fastly grew from a Kickstarter project to a global player when it comes to inverse stereolithography. Formlabs provides 4 different iSLA printers, 1 SLS machine, and a post-processing system. The latest model is the Form 3, which comes in 2 sizes. The desktop model costs about $3,500 and is the cheapest of all Formlabs models. It has a building volume of approximately 2 liters. The layer thickness can be varied between 25 microns up to 300 microns, and the laser has a power of 250 milliwatts with a resolution of 25 micrometers. Its bigger brother, the Form 3L, is about $10,000. The building volume is 10 times bigger, but layer thickness and laser power stay the same. Those are only the prices for the SLA systems. For the post-processing station, including washing and post-curing device, another $2,500 need to be invested. Formlabs is present in many industries and has customers all over the world. As SLA parts are highly detailed and fulfill highly demanding surface properties, there is almost no limit on where the parts can be used. Depending on the field of application, the later part has to have different properties. Therefore, Formlabs offers a material library, each material specifically designed for the application. One of the biggest customers is the medical and dental industry. Formlabs supports the idea that every medical facility should have the opportunity to print customized parts directly at site. Therefore, they provide biocompatible resin formulas which can be used for dental implants or hearing aids or even prostheses. But they also provide special resin formulas for strong or flexible parts for functional prototyping, castable resins for jewelry, and different colors for each of them. If you're interested on what Formlabs offers besides iSLA, I recommend to visit their website. You can request many documents and materials by simply providing your HBAS email address, and you can even take part in free webinars. If you're interested in what is possible with SLA even further, I recommend the TEDx talk, What if 3D Printing Was 100 Times Faster? It explains how oxygen barriers can be used to continuously print parts with inverse SLA in only fractions of the usual time. If you want to recapture what I just told you, I prepared a little handout. You can download it from Leia and you can find every important key concept there, so you don't have to watch this video again. You can also find my references, literature recommendations, and some interesting web links there. That wraps up my part of this presentation. Now it is your turn to take action. As I said in the beginning, I prepared a little Kahoot quiz. It should not take longer than 3 minutes. I will post the link in the Zoom chat, and if you want to take part, just try it out. I can't wait to hear your questions later on. Thank you for watching and see you in Zoom.